So at psi 2, you should get this kind of output. Okay? At psi 2, you should get this kind of output. If you have 0, 0 as your input, 0, 0 as an input means that you have 0 here, 0 here. Okay? Then the output should be 0, 0. Okay, because if it's 0 here, okay, then the first thing should be 0. The second thing is y is 0. 0 modulo. So it should be 0 f of x, which is 0. Okay, the output due to 0, 0 input will be that. Okay, if it's 0, 0, 0 here, you have 0 here, and 0 plus f of 0 over there. This should be your output. Okay? And then the second input, if it's 0, 1, 0, 1 is your input. Okay, 0, 1 as the input means that you have 0 state here, 1 here. Okay, that means that you will have 0 state in x gate and then 1 state in the y line. Okay, 0 state in the x line and 1 state in the y line. This is what 0, 1 means. This state times that state. Okay, this is belonging to x. This is belonging to 1. Okay, then if you look at that, then the first term should be, because of the minus sign, it should be minus 0, 0 will give you 0. What is the second? What is the 1? What does this second output correspond to? Y is equal to 1, right? 1 modulo 2 f of 0. This is the one that corresponds to this input, which is equivalent to this times that. Okay, this is coming from x, that's coming from y. So the second output should be that. Okay, and then the third term is 1, 0. This 1 is coming from here, 0 is coming from here. So this is x, this is y. So this is my x, this is my y, and then the third term should be something like if I have 1 and then 1 plus y is equal to 0, right? 0 plus f of 1. Okay, 0 plus f of 1. It's a third term. And then the last term, the last term is due to 1 from here and 1 from there, give you minus 1, 1. So x is 1, y is 1, so I should have x is equal to 1, y is equal to 1, 1 plus f of 1. So these are my 4 terms after it goes through this thing, and these are the 4 outputs. So if the first operation is 0, it actually does nothing to the second bit. Okay? If the first operation is 0, in this modulo addition, the second bit doesn't matter. So you can actually remove this, because it does nothing. It just becomes F1. Okay? So there are 2 kinds of functions that you can put in this algorithm. You can have fx is equal to constant. X is equal to either 0 or 1. Okay, the input is equal to 0 or 1 because it's a digital signal. X is equal to 0 or 1. F is equal to constant means that f of 0 is equal to 1, f of 1 equals to 1. So Okay, f is a constant function. So which means that f of 0 is equal to f of 1. And if this is the case, what does this become? Okay, psi of 2 is equal to if f of 0 is equal to f of 1, then I would have this been, this I can also delete, I believe. This I can also delete because it does nothing to the bit. Okay, so I can rewrite the thing as being equal to 0 f of 0 for the first term. And then this is the case when it's a constant. If fx is a constant function, minus 0. And then f of 0, okay, is either 1 or 0. And actually, f of 0 is 1, f of 0, actually I didn't say this correctly. F of 0 is a constant function, means f of 0 is always equal to f of 1. It can be 0 or 1, doesn't matter. So this is not correct. This is true always. Okay. The output can be f of x should also be equal to 0 or 1. But then when it's 1 for the other one, it's also 1 for the other one. It's 0 for the other one, it's also 0 for the other one. Okay. So if that is the case, then I will have the second term remaining as 1 plus f of 0. Okay, because this thing can be 0 or 1. Okay, and then the third term is 1 f of 1, but f of 1 is the same as f of 0. So I can put this as f of 0. Because it's a constant function, it always follows the values of the other argument. That's what the constant function means. Okay. And then the last term, I can also write this as f of 0 minus 1 plus f of 0. Okay. I can write everything in terms of f of 0. And then if I write it in this manner, then I can factorize this now. I can factorize this as product of two terms. 1 over 2, 0 plus 1, multiplied by f of 0 minus 1 plus f of 0. Okay, I will get all the four terms there. Let's check if it's correct. This term times this term gives me the first term. Okay, this term times this term gives me the second term. This term times this term gives me the third term. This term times that term gives me the last term. So I can factorize size of 2 as products of two terms. Okay? As products of two terms. And then this belongs to the lower line. Okay, this belongs to the upper line. Because when I took this, I always taking the second factor. I'm always taking the second factor. So this must be belonging to the lower line. This belonging to the upper line. So when I apply the Hadamard gate, it will only affect the upper line. It doesn't affect the bottom line. Okay, so psi 3 constant is equal to, if I work it out after this has been operated upon by the Hadamard gate, okay, it becomes a 0. I don't know if I have it anywhere. But if you apply the Hadamard gate to this, it becomes a 0 state. Okay? and then I get 0 multiplied by, there's a root 2 somewhere coming along, times this one. The bottom state doesn't change. I just get 0. And then you go through the same operation again, assuming that fx is balanced. Fx is balanced means that f0 is always equal to not f1. When this is 1, this is 0. When this is 0, this is 1. That is what it means. And you go through the same operation again, you find that psi 3 balance is equal to 1. 1 over root 2. The same state goes in here. Okay. So the marvel of the Deutsch algorithm is that at this stage, you do not know what f of x is. Okay, f of x can represent a constant function or a balanced function. It's a constant function or a balanced function. But then, just with one operation at this stage, you can figure out whether it's balanced or constant by just looking at the state of the first bit. Okay, the state of the first bit tells you that if f is a constant function or if f is a balanced function, just with one operation. Whereas if you have a function f of x, in order to decide if it is balanced or constant, what you need to do, you need two operations. You need to operate f on 0, you need to operate f on 1. And then you look at these two results and decide if f of x is a constant or a balanced function. But this one just needs one operation. And then you just operate on that. You can change the f in this thing, you just operate once. It will tell you whether f is balanced or constant. It's like flipping a coin. Okay? If you have a coin with two faces that are different, you need to flip it 2 times to decide if the coin is same face on both sides or different faces and different sides. But this says that you only need to flip the coin once. Okay, if you change this f over here, you just need one operation. So this is an example of quantum parallelism, a very simple example of quantum parallelism.